Hello. So I've been growing plants in my room, and it's been kind of a pain to water them, especially when I go to school because I need to bother other people to water my plants for me. So I think the best way to go about it is to somehow figure out how to automate a watering process. The most effective thing would be to use like sprinklers, like people conventionally use, but I can't really do that because that's in my room, and I also have grow lights, so I don't want those getting wet. So the approach that I'm going with right now is some sort of flood tray. So basically, I'll have the plants sitting in this little thing right here, and this will lay across the wire mesh. And then in this little box down here will be some sort of like bulkhead with a tube going down to a lower reservoir just to store all the water, and then the water will just pump back in. And it won't be on all the time, it'll be like probably once every 2 days or so, just to water the plants. And I want them to flood to about a height of like half an inch, so that the plants don't get like, the water level doesn't get too high, but they get enough height so where they can suck up the water. So this is like some of the stuff I was thinking of when I was designing this. So I want the goal to be to get the upper tray to flood at a height of about half an inch or so. And how am I going to do this? I'm going to change flow rate of water in, or change the drain hole size. So I can achieve this by either in a steady state where the water level remains at some sort of equilibrium at the desired height, or I can achieve this by just turning off the pump at like some sort of time when the desired water height is reached. For that, it'd be like the inflow rate will be just much higher than the outflow rate. So I guess I'm gonna go with the equilibrium one because it'll like decrease the amount of flow rate that I'll have to have on the pump. And of course you gotta set the sources, so there's that. And yeah, I'm gonna start by like just determining the amount of force that will be required on this lower tray down here, just to see if it can hold the water or not. But anyway, this is the equation for pressure at a given height below a water level. And right here, atmospheric pressure is negligible because both sides of the platform are exposed to the atmosphere, so it gets contributions on both sides which cancel out. But of course, force equals pressure times area. So if you consider the area of the lower tray, it's multiplied by the pressure that's exerted on it. I can see that I should expect about 5.4 pounds, which is pretty reasonable. So I don't see a design flaw with that. And then now to get the water to about 4.5 inches, and this is the height because I'm using 2x4s, so it has to go 4 inches from here and then about half an inch above so the plants get the water. But anyway, I'm going to start with the mass balance. So of course, density equals mass divided by volume, and then that eventually gets me to a volume balance. So at steady state, change in volume equals 0, which means that volume in equals volume out. And now we can use Bernoulli's equation to determine volume out because it depends on the height of the water reservoir. So this is the overall equation, and then we can make some assumptions which reduce this. So an assumption you can make is that the top layer of water, you could assume that the flow speed is negligibly small, which is reasonable because cross-sectional area of the overall reservoir is much greater than the outlet cross-sectional area. And also they're both exposed to atmospheric pressure, so P1 and P2 cancel out. So the equation reduces to this, and then I can solve for the flow speed to be this, and then the volumetric flow rate is equal to cross-sectional area times the flow speed, so it equals this. So this is our V out, and then from our volume balance we know V out equals V in. So this is our V in to satisfy our height requirement. And then if I'm planning on using half an inch diameter bulkheads, I just plug in for area, and I can expect to get about 3 gallons per minute of flow rate in if I want to use those half-inch diameter bulkheads and still reach a steady state of 4.5 inches. And you may ask, at what time will this equilibrium be reached? And this is important because I want to know when I should turn off the Arduino that's going to be controlling the pump. So now to get the water level to 4.5 inches, I can start with my volume balance, and we can now use that the volume out is equal to the area times this, where h of t is some sort of arbitrary height at a point in time. And we got this from up here, which V out is equal to this. This is like the max V out, but this gives a V out at any point in time. And since we already said that the V in equals this to give a steady state, we can just plug in both of these into the volume balance. And then we can consider the volume equals height times length times width. And we can just substitute that in for volume here. And the only thing that is changing is the height of the water level. So we can just pull these out as constants and then divide both sides. And we have a differential equation that gives us the change in height for a change in time. And yeah, you can solve this. I'm going to just solve it numerically. And if you put it in MATLAB, it gets a graph that looks like this, which makes physical sense. And it basically means that I can expect to turn off the water and get a height of about 4.5 inches after about 100 seconds or so. And you may ask, how can I make it reach this equilibrium position faster in time? And you can do that by changing the parameters here. So you can change how big the reservoir is, or how big your outlet is. And you can see by changing those, you can get a much faster steady state, which is also at the same height of 4.5 inches above the water. Thank you for watching.